So continuing with chapter 1, structure and bonding, this short video will tell you how to draw Lewis dot structures and also why the bonds form. Okay, let's talk about a little bit about the development of chemical bonding and theory. It was in 1800s, middle of 1800s, that Kekulé and Cooper, they had independently proposed that in all organic compounds containing carbon, carbon always forms 4 bonds, that it is tetravalent. However, they were looking at the structures in a two-dimensional form. But later on, Van 't Hoff and Liebel proposed that they added actually a third dimensions to the organic compounds, and they said that the 4 bonds of carbon are not oriented randomly, but they do have a specific orientation, spatial direction. And they suggested that actually the 4 bonds are situated at the 4 corners of a regular tetrahedron, and carbon sits in the middle. So this is a representation of a compound where carbon is in the middle and it has attached to 4 hydrogen atoms. They proposed a structure of a tetrahedron, regular tetrahedron, where the dashed bonds represent the bond that's going behind the page. These solid bonds, they represent bonds in the plane of the page, and this wedged bond is a bond which represents the atom, or the atom that is bonded to carbon coming out of the plane. The next question that comes to our mind is, why do atoms form bonds? That is a relatively easy question to answer, because atoms form bonds so that they can form compounds which are more stable than the separated atoms. In general chemistry, you have learned about 2 types of bonding: ionic, which is formed as a result of electron transfer. One very common example that is you often cited while explaining ionic bonding is sodium chloride, where sodium loses an electron and chlorine gains an electron. As they both achieve an octet, makes the compound sodium chloride more stable than the individual sodium or the chlorine atoms. The second type of bonding is covalent bonding, where the electrons are actually shared between 2 atoms, and this was proposed by G.N. Lewis in 1916. The whole collection of the neutral collection of atoms held together by covalent bonds is what is called, ends up in a molecule. A simple way of indicating the covalent bonds in molecules is by Lewis structures, which represent the valence, in which the valence electrons are represented as dots. So for example, hydrogen, if you recall, the electronic configuration of hydrogen is 1s1. It has got 1 valence electron, so it's the Lewis dot structure, it would be represented by 1 dot. Okay, so in this manner. Now carbon has electronic configuration is 1s2, 2s2, 2p2, right? It has got 4 valence electrons, so carbon will be represented by 4 dots. Nitrogen has electronic configuration 1s2, 2s2, 2p3. It has got 5 valence electrons. So nitrogen is represented by 5 dots: 1, 2, 3, 4, and 5, and so on. Okay, so if you look at the structures that are represented here, the molecules are represented here. This is methane. The Lewis dot structure will have carbon in the middle, the hydrogens each with 1 valence electron, and the carbon's valence electrons are indicated by the green dots. And similarly for ammonia, in NH3, you have nitrogen's 5 valence electrons represented in blue color, and hydrogen 1 valence electron represented in green, and so on. There is another way of representing the covalent compounds, and that's through Kekulé structure, where a line or a bond is drawn between the 2 electrons that form the covalent bond. So for example, this is again methane, can be represented in this manner, ammonia in this manner. Any valence electrons which are not used in the bonding are then represented as a lone pair or a non-bonding pair on the molecule. So here again, water, if you look at, it forms 2 covalent bonds to hydrogen and then the 2 lone pairs on the oxygen, and so on. Now, how do you know how many bonds each of these atoms form? So the number of covalent bonds an atom will form will depend upon how many more valence electrons it needs to reach the noble gas configuration. So for example, carbon has 4 valence electrons, but it needs 4 more in order to reach the configuration of the nearest noble gas, which is neon, right? So same thing with nitrogen. Nitrogen has 5 valence electrons. It needs 3 more to reach the configuration of neon, which is the closest noble gas. And oxygen needs 2 more electrons, and so it forms 2 bonds. So if you look at the next slide here, carbon's valence electron 2s2 2p2, it forms 4 bonds in this manner. Hydrogen forms 1 bond, nitrogen forms 3 bonds, oxygen forms 2 bonds, and then all the halogens form 1 bond because they need only 1 more electron to complete its octet. Okay, so that helps you to decide how many bonds each of these atoms form. This is very important. I would like you to know how many bonds each of these atoms form in their neutral state. Okay, so that means if the compound is not charged, if it is not an ion, then how many bonds each of these elements can form in their neutral state. Again, as I talked before, the number of electrons which are not used in the valence electrons which are not used in bonding are called as non-bonding or lone pair of electrons. So here we have a pair of electron and nitrogen in ammonia where they were not used in bonding, so they are left alone as lone pair of electrons. Okay, so this is your Kekulé structure where you represent the ammonia in this form. This is the Lewis structure. Some other ways by which carbon can form bonds. So like we said, it forms 4 bonds, right? But it doesn't always have to form 4 single bonds. It can form 4 single, or it can form 2 single and 1 double, which is also an indication of the valency of carbon as 4. It can also form 2 double bonds. It can form 1 single and a triple. And then it can also be represented as a charged species where it can form 3 bonds. And if a pair of electrons are left on carbon, it gets a negative charge. We give it a name. It's called as a carbocation, which you will study later on. However, these are the different ways by which carbon can form bonds. Similarly, can you think of different ways by which nitrogen and oxygen can bond? In the next. So some ways by which the nitrogen and oxygen can form bonds are shown in this slide, where nitrogen can form 3 single bonds with a lone pair of electrons, or it can form a triple bond and a lone pair of electron, or it can form 4 bonds where it has actually used this lone pair of electrons, and that gives a positive charge to nitrogen. Okay, so this is a charged species. Oxygen similarly can form 2 single bonds with 2 pairs of electrons, or it can form 1 double bond with 2 pairs of electrons, or it can form 3 single bonds and use up one of its pair of electrons to form a bond, and as a result it gets a positive charge. Okay, and or it can also form a single bond, 3 pairs of electrons, and then it gets a negative charge. Okay, so one example we can write to show this more clearly is where in Chem 152 you must have studied about hydronium ion, right? So this is a very common example to show oxygen having a positive charge. This is H3O plus hydronium ion. This can be represented by OH, right? Hydroxide ion. So if you recall, where oxygen forms 1 single bond, right? Sorry, let me redraw this. So where oxygen is forming a single bond to hydrogen, so OH, and then you have the lone pair of electrons and oxygen giving it a negative charge. So these examples you can recall from general chemistry. Similarly, this here we can, a very common example is that of ammonia. Okay, so here we are going to work out a problem just to check your understanding. It's asking you what are the likely formulas of the following molecules: carbon, F2, and then a chlorine, right? So we have to tell how many atoms of chlorine will be there in this molecular formula. So you recall that carbon forms 4 bonds, right? So we write carbon with a fluorine and then the other fluorine, and then we have one chlorine, right? But then it has got, we have to find out how many chlorine should be there. So since it has forms 4 bonds, so you should have 2 more chlorine. So the formula should be CF2CO2. Now for this one, can you take a guess of how many hydrogens should be there in this molecule? Now remember again, this is a neutral molecule, right? So in its neutral form, carbon likes to form 4 bonds, but at the same time, oxygen likes to form 2 bonds, right? So you should first finish off drawing 2 bonds to oxygen, and then hydrogen, likes to form 1 bond, but then we are allowed to choose how many hydrogens it can have here. So it will have 1 more. So this will be the formula, and CH2O, and that covers the carbon's 4 bonds, 1, 2, 3, 4. Oxygen likes to form 2 bonds, and then hydrogen 1 bond. Then to complete it, we should actually draw the lone pair of electrons on the oxygen so that it represents a full Lewis structure. Okay, so this is not part of, we don't have, the question is not asking you to draw this, it's just asking you what could be the formula. So the answer is, this is the formula and this is the, okay. Let's look at the next.